Good morning, everybody, and thank you for the welcome. First of all, before I begin, I'd just like to explain that my presentation contains many points and many words, which I will say, so there's no need, unless you want to follow, to read the words that are on the screen. So, but the other thing I'd like to point out is that because of the limited, this PowerPoint presentation contains a little bit more information than is in the printed document. So you might like to pay a little bit of attention. So anyway, I will try to get through the points. The main thing is that the points that I want to cover are on the slides. So, as an introduction, in Australia, the Australian standard specifies that in order to minimise the risk of failure due to nickel sulphide, toughened glass must be either laminated or heat soaked in accordance with the European standard. Now, it also notes that heat soaking will not totally eliminate the small risk of fracture due to nickel sulphide, and consequently laminated glass is very frequently specified by specifiers for buildings in Australia. And unfortunately, in spite of laminated and heat soaking, we continue to get breakages in Australia. So my presentation will be more of a practical experience of what we've experienced on site and some information about what I've found with nickel sulphide compositions. So the fracture origins that, because it's laminated glass, we have been able to capture the fracture origins in many of the recent cases, and the examinations have revealed the size and the shape of the inclusions were typical of nickel sulphide, and this was confirmed by the CSIRO, this Commonwealth Scientific Industrial Research Organisation in Australia, and it was confirmed, and this was a very small nickel sulphide inclusion which resulted in failure of a fairly large panel of glass and 0.15 millimetres. And you can see many cracks coming from the inclusion. And then we discovered different areas of the inclusion had different compositions of nickel sulphide. And so it varied over the surface of the glass, and so we really, as a consultant, we need to know a lot more, and that's why I'm here at the conference, to learn a lot more about it, and hopefully Andreas Kasper, next speaker, will be able to shed some light on what I'm saying. But so the Spectrum 1 showed similar compositions and Spectrum 6, and sulphur was 54% of that but then other areas was less sulphur. So Spectrum 10 was only 48%. So there is a distinct variation over the surface. Now these differences may shed some light on why the heat soaking carried out was not successful. So the glass was specified to be heat soaked and laminated tempered glass, and yet we got breakage. So in view of the numbers of breakages experienced in these projects, it appears that the glass was either not heat soaked properly, or there was some other reason, or they didn't heat soak it at all, even though they claim they did. So a method for checking if heat soaking was carried out would be a very useful tool. And what I've been working on is to try and analyse whether or not it's possible to look at a broken piece of toughened glass and see whether it was heat soaked or not. And so I'd like to present just briefly, everybody here probably knows the theory of toughening, and it's heated to very high temperatures and quenched, And so the surface is hardened before the centre, and then when the centre hardens and cools and contracts, we result in residual surface compression and centre tension. So there's methods for differential surface refractometers and other grazing angle surface polarimeters for measuring the surface compression stress. And more recently, there is the scalp is used for analysing the stress through the thickness of the glass. So the thickness of the glass is the stress variation through the thickness is now able to be actually measured by photoelastic means. So spontaneous fracture, as was mentioned previously, one of the many possible causes is nickel sulphide, and there can be other causes. I've analysed many breakages, and surface scratching has resulted in spontaneous fracture, and in many cases. And people send me a fragment and say, "Oh, look, there's nickel sulphide," and I say, "Let me have a look." It was a scratch. So it's not always nickel sulphide. The mechanism for spontaneous fracture has been explained previously by many researchers, and this phase, as our first speaker mentioned, the phase change from alpha to beta is with the expansion is what causes the extra stress, and whether a particular nickel sulphide inclusion results in fracture depends upon the factors such as its size and its position within the glass, whether it's in the centre tension or closer to the surface and as was mentioned by a previous speaker, Swain derived a relationship for the critical size of the nickel sulphide inclusion, and using a parabolic stress distribution. Now figure 1 shows I calculated the size of the nickel sulphide, the critical size depending on the stress. So if, for example, if the diameter of the nickel sulphide inclusion is only 0.1 millimetres, then you need a stress of 35 megapascals for that size of inclusion to result in fracture. And I'm not sure whether our previous speaker has taken that into account in the probability calculations. So heat soaking is carried out to affect the transformation, and it involves putting the glass through a secondary heating, as we all know. And in Australia, it was specified the European standard, and the temperature has recently been, the European standard has been changed to 260 degrees, a lower temperature, and which is more likely to capture all of the different types of nickel sulphide for breakage in the heat soak testing. And but the recent breakages that we've had in Australia, it has been admitted by at least one of the manufacturers that they did heat soak to the old standard, and that may explain why we still continue to get breakages. But anyway, the results presented later were based on the temperatures I used for this example calculations. I used the 290 degree maximum temperature for my calculation of the residual stress. So, the fracture characteristics of toughened glass, as we know, it fractures into small fragments, and the size of the fragments depends on the tensile stress in the centre of the glass. And the crack tip speeds up, and when it reaches a certain speed, it will fork into two cracks and slow down, and then it will speed up again and fork into two cracks. And this was why you get the higher the tensile stress in the glass, the smaller the size of fragments. And so the cracks accelerate, slow down, and form the fracture pattern that we see. So for crack velocities greater than 60% of the elastic shock wave, the maximum principal stress is located at 60 degrees. And this is why we tend to see hexagonal fragments at the fracture origin. So the fragment size is also inversely proportional to the energy stored in the glass, and this also explains why, for the same tensile stress, in thicker glass we see smaller fragments because there's more energy there to break the cracks into smaller cracks. Also, toughened glass which has undergone heat soaking tends to have larger fragment sizes. Now this is something we've observed over many, many years, and therefore stress relaxation obviously takes place during the heat soaking process. And so it's calculating the degree of stress relaxation that is really part of this presentation. It's a very difficult exercise, and we didn't. The data available is very limited on the viscosity and temperature and composition, all of those things. The degree of stress relaxation depends on the viscosity of the glass, and it also depends on the glass composition, the temperature of the glass, and all of those other factors. And the question is often asked, is glass a solid or is it a liquid? And the answer, of course, is it's complicated, but it's both solid and liquid. And in fact, in my research, I've found even at liquid nitrogen temperature, there is a viscosity, and it's measured. And I've found some references. I've got it on one of these slides. But it's under high pressure. And so the viscosity describes a fluid's resistance to flow. You can read the paper. I'm running out of time here. I'm looking at the clock down here. It's winding down very, very fast. And so the viscosity is constant for a given temperature and is independent of the shear stress, which should not be confused with the viscous forces that arise during. So the problem is that glass behaves as a non-Newtonian fluid, and the viscosity changes with pressure in the glass. So at these indentation hardness testing that they carried out at liquid nitrogen temperatures, very, very high pressures were applied, something of the order of just a simple calculation, 4 gigapascals, and very, very high stress. And the glass didn't break, but there was a flow, and you can measure the hardness and viscosity, and it has been measured at very, very low temperatures. And so non-Newtonian thinning fluids have a viscosity which decreases with agitation and then settles down into a nearly solid state when at rest. And shear thickening fluids increase. It's the opposite. So the problem, we have non-Newtonian behaviour of glass, soda lime silica glass, and that's what the consequence of the non-Newtonian behaviour is what enables the stress distribution in toughened glass or tempered glass will change, because the stress in each layer of the glass is different, and therefore we have different flow rates. And so what in fact happens during heat soaking is that there's a change in the stress distribution. It's no longer parabolic, but it flattens out in the centre, and that explains why tempered glass has larger fragment sizes after it's heat soaked, much, much larger than you would expect by measuring the surface compression. Surface compression tends to change very, very little, only 3 to 5 or even 10% at the most, but the centre tension can reduce by up to 50% depending on the behaviour. So very little data was available for the temperature range at which heat soaking is carried out. I searched through all the literature I could find. And that chart shows the data I was able to find, where generally at heat soaking temperatures we think very, very high viscosities, and yet at these indentation hardness measurements, you've got viscosities very, very low under high pressure. So from various sources, and you can see here freshly drawn fibres, fiberglass, followed a line down there. Whereas most references that you can find, the viscosity increases so much that you would expect very little to happen during heat soaking, but in fact it does because of the stresses in the glass. So just pushing along very, very quickly, since I'm running out of time very fast and I'm only a short way through the talk. Various researchers have investigated the degree of stress relaxation in toughened glass which occurs during heat soaking, and one has reported 10% in 1 hour at 300, and some have reported only 3% in 4 hours, or 5% in 24 hours at various temperatures. So surface compression doesn't seem to change very much. But none of these researchers reported the stress relaxation in the tensile zone, even though the Danish paper that I saw, they had the stress measuring equipment able to measure the centre tension, but they didn't report it in that paper. And so I've postulated that the stress distribution through the glass thickness is flatter at the centre after heat soaking than the original distribution before heat soaking. And I've calculated only by a first order approximation at this stage, so we need further work on the procedure. But I've used a mathematical relationship, just a simple relationship to describe the stress at any position, and just a simple power law relationship where the stress at any position x equals a constant A times x times a power p. So this relationship holds only for positive values of x, and therefore 0 is at the centre of the glass, and my calculations were carried out for half the glass so that the mathematics works okay. And so the exponent p is always positive, and c is the tensile stress at the centre of the glass, which is positive. And I've done some calculations for using this equation on the next slide, and it shows what we expect for equilibrium is that the area A1, which is the tensile area, must equal the area A2, which is the compressive stress area. And so that relationship, A1 must equal A2 for equilibrium, is what leads, I found a very interesting, A1 must equal minus A2 because of the mathematics. And the distance from the centre to the point where the stress is 0 is x1, and the compressive stress at the surface is S in the equation, which has a negative value, therefore P. And then by integrating the mathematics, just by simple integration from naught, which is the centre of the glass, to x1, and then by integrating from x1 to the surface, and juggling all the equations that come out of that, it was interesting to find the simple expression where the power is equal to minus surface compression divided by centre tension. So a simple relationship. So if it's a parabolic distribution with the power equals 2, it gives you the centre tension is equal to half the surface compression. Simple relationship, and it works for any other distributed. So that kind of simplified the thing a lot in the mathematics. But then, as I said, really the unknown factors are the actual viscosity values to use at the different temperatures and the different stresses. So these are, by following through those calculations, these are the equations that I was able to derive and use for the estimation of the relaxation in each layer of the glass. And assuming that relaxation is proportional to the remaining stress, gives the Maxwell's relation law, gives that equation, which we won't go through in detail here. You can read it all later. And that leads to the, for the purpose of the paper, I assumed that the viscosity changes with temperature by that equation, and where the temperature of the glass in degrees C, and then the viscosity is lower for glass subjected to stress for a given time. It was assumed that the reduced velocity can be determined from the expression, expression there, where the logarithm of the viscosity is equal to the original viscosity minus the time and stress that it's at that stress. So, and since I wrote the paper, I found another reference that said, in fact, there's another relationship which I'll show you at the end. So I'll buzz through this since I've only got 2.5 minutes left. The stress distribution was reduced. When at room temperature, you may have a surface compression of 90 megapascals and a centre tension of half of that, 45 megapascals. But when you heat the glass to the heat soaking temperature, the stresses are reduced because the glass is expanded and the stresses are reduced. So you have the relaxation is calculated based on the actual stress at the temperature of heat soaking. Not at room temperature stresses, but at the stress at the heat soaking temperatures. And so we can get a greater stress relaxation in the surface compression layers than in the centre tension. And so A1 dash and A2 dashed are the actual calculated relaxed areas, which are then a different area. So it was a little bit tricky, and my mathematics may not be precise, and there'll be a lot of students available at this conference and in future who will be able to calculate the mathematics a lot more accurately than I have. And then it was important to, we didn't know exactly the relationship, whether it's the centre tension or the surface compression. So I assumed in the calculations that C minus S was constant, and then used an average area. So this is what we have. The original stress in the glass is the blue one, and then the lower one here is the stress distribution in the glass at the heat soaking temperature of 290, and then that gave you the relaxation. The difference there was the relaxation in the stress at that position, and the grey one is the final solution after it got down to room temperature. So when it finally reaches room temperature, the grey one is the distribution, and you can see from this that it is flatter, and even though the surface compression has only reduced by a few percent, the centre tension has reduced by a lot more. So there's a lot more that can be said, but what I just quickly, having reached zero on this, 20 minutes is up. The results in figure 4 show that after heat soaking at 290 for 2 hours, for an assumed surface compression of 79.6 megapascals after heat soaking, the depth of the surface compression layer was reduced to 1.7 times millimetres. That is 0.14 times the glass thickness from the original depth of 2.5 millimetres, which is the 0.211 times the thickness of the glass. So quite a distinctive difference. However, if only 5% reduction in surface compression is assumed, as was found by some researchers, then the result, as shown in the following slide, and in this case the surface compression layer was reduced to only 1 millimetre thickness. Quite a different and a much bigger relationship. So that was the result then for and here it was more like P equals 4. So that power profile was 4. So this is only, I must emphasize, this is only the first step. All I've done so far is, as I mentioned earlier, here is a graph that I found after I wrote the paper and submitted it. So the strain rate is, it's really, if you plot the viscosity versus the strain rate, and that's on a logarithmic scale, it's not exactly I've assumed a 1-to-1 ratio in my calculations, but it looks like it's a 1 to a logarithmic relationship. So there's potential for a lot of improvement in my calculations, but I've been able to demonstrate that this is the reason why we see such a difference between the surface compression and the surface and the centre tension. And so what I've concluded is that due to the non-Newtonian behaviour of glass, the viscosity of the glass is lower when it is subjected to higher strain rates or applied tensile or stress in its viscoelastic state. Therefore, there is a difference in viscosity between the tensile layers of the glass and the greater compressive stress layers of the glass, and the difference leads to stress relaxation rates in the different layers of the glass when it is undergoing a heat soaking process. And therefore, this results in a change in the shape of the stress variation curve through the glass thickness, which results in a smaller depth of the surface compression layer in the glass which has been heat soaked. And therefore, it is feasible, in my opinion, to determine by looking at the broken glass if the glass was in fact heat soak tested, because the surface compression layer is much thinner. But I point out much more work is required to confirm, because I don't have the exact figures for viscosity. My calculations were only a one-time step. You could really improve the calculations and improve and find out the relationship between the time in the heat soak oven and the stress distribution curve. So thank you for your attention. Sorry, there's only about 2 minutes left for questions.
Thank you, Ignatius.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.